Hello, my name is Philip Lynch. I'm a PhD candidate studying remote sensing and Thermal Reynolds Geoinformatics Lab at York University. The name of my presentation today is Satellite Remote Sensing Post-Fire Regeneration Assessments, which is a research selection taken from a larger survey conducted by Thermal K. Remel and I, focusing on the 2003 Okanagan Mountain Park fire. In most parts of Canada, fire is a significant stand-replacing disturbance, and monitoring large-scale post-fire recovery by satellite remote sensing is a major research area. Frequently, these efforts implement spectral vegetation indices, specifically the Normalized Difference Vegetation Index, NDVI, and the Normalized Burn Ratio, NBR, to assess forest regeneration trajectories. It has been observed that the Infrared Vegetation Index, VIIR, exhibits a stronger correlation with biophysical properties of vegetation, specifically stages of stand development, compared to, for example, NDVI. Okanagan Mountain Provincial Park, the study area as seen mapped to the right, is a temperate forest located in the southern part of the province of British Columbia, Canada, in the semi-arid Okanagan Valley near the land border with the state of Washington, USA. On August 16, 2003, a lightning strike hit the forest on Okanagan Mountain. This triggered a wildfire at nearby Rattlesnake Island, which was fueled by a constant wind in one of the driest summers in the past decade. It was estimated that the fire burnt roughly 250 square kilometers, an area containing a majority of the park's trees. The study area perimeter was hand-clipped to roughly 240 square kilometers by removing urban areas in the north. The Canadian Digital Elevation Model was used for image corrections of topography. Landsat 7 ETM Plus Level 1 data for August 5, 2007 and September 30, 2010 were acquired for the study. ATCOR 2.3 was used to direct imagery for atmospheric and topographic effects. Multispectral data were corrected to top of the atmosphere reflectance. Brightness temperature was corrected to land surface temperature. Gaps resulting from Landsat 7 scanline corrector failure were interpolated to maintain data integrity and cartographic display. Interpolation was performed on spectral index data calculated for each year using the geostatistical wizard in ArcGIS after converting each image to a series of points. Methods of interpolation include ordinary kriging and co-kriging using both semi-variogram and covariance with the K-Bessel model. Co-kriging interpolation of the 2010 image was performed using the 2007 image as a predictor. According to best assessment of the 2010 data, NDVI was best interpolated with co-kriging, and NBR and VIR were best interpolated with kriging. NDVI has been used successfully to identify regeneration after fires, where yearly satellite images are adequate to distinguish changes over time. NDVI may act as an indicator of canopy growth structure, photosynthetically active radiation, and vegetation's light absorption properties. The equation normalizes the difference between the red and near-infrared returns for a pixel by their sum, resulting in a range of values between -1 and 1, with higher positive values indicating greater chlorophyll abundance. NBR uses a formula similar to NDVI, giving values from -1 to 1 to quantify the severity of a fire, leveraging shortwave infrared and near-infrared wavelengths. Burned areas provide high reflectance in shortwave infrared and low reflectance in near-infrared. In contrast to NDVI, lower NBR values indicate recently burned and bare grounds, while higher values indicate healthy vegetation. However, while these indices are sensitive to changes in plant condition, they are also limited by the presence of smaller vegetation such as forbs, grasses, and non-woody pioneer flora, which quickly fill post-disturbance space, yielding fast saturation to pre-disturbance index values. It has been observed that vegetation indices incorporating both shortwave infrared and thermal infrared wavelengths exhibit stronger correlations with biophysical properties of vegetation compared to indices not incorporating both wavelengths. Most specifically, Boyd et al. 1996 implemented VIR to assess regeneration stages of Amazon rainforests according to how long they had aged after deforestation based on a low-high range of values. Compared to NDVI, VIR was found to boast a significantly higher correlation with plant biophysical properties, specifically stand age. Correlation coefficients increased from 0.26, 95% confidence with NDVI to 0.93, 99% confidence. Fractional vegetation cover estimated by remote sensing is a primary method globally. Fractional vegetation cover as an NDVI-derived spectral vegetation index has shown to be useful for studies of vegetation condition as well as hydrological, ecological, and other environmental change such as alterations in vegetation coverage affecting soil erosion. A significant correlation has been observed between NDVI and surface fractional vegetation cover in desert, steppe, meadow, and mixed vegetation areas. Here, NDVI-S is a value for bare ground, and NDVI-V is the value for a fully vegetated pixel. It has been specified in research that NDVI-S be derived from the inflection point of an NDVI histogram. The inflection point for the study area was determined to be 0.21. NDVI-V is assigned the maximum index value of the region. For the 2010 data, mean index values were calculated for 5 equal area classes of fractional vegetation cover and compared to the soil line index. Soil color is quantitatively aligned with soil reflectance, and the amount of light absorbed fluctuates with soil brightness. The red near-infrared ratio is contingent on biomass and density of the green vegetation. The presence of vegetation over soil results in a decrease in red band reflectance due to chlorophyll absorption and an increase in near-infrared band reflectance due to mesophyll structure. Directional deviation from the soil line may, therefore, be attributed to plant biomass in addition to soil properties. The soil line index may be interpreted as a measure of soil brightness. It is assumed that there is one soil line encompassing a majority of soil types and surface conditions. The soil line of remotely sent soil spectra characterizes soil type, defines vegetation indices, and may be used to correct reflectance assessments from optical soil effects. The soil line may be calculated as a spectral index with a simple regression formula calculated between the near-infrared and red bands. Moreover, red reflectance values often deviate largely among soils as compared to the near-infrared reflectance parameters. Yet red and near-infrared reflectance pairs plot linearly because incoming light is reflected proportionately to those parts of the spectrum. Here, mean index values have been calculated for 5 classes of fractional vegetation cover high to low. Those mean values, referring to the y-axis, are plotted against the soil line index on the x-axis. All 3 indices possess a linear association with the soil line, and larger fractional vegetation cover percentages show less soil brightness, assuming greater canopy cover. There is a significant distance between the high fractional vegetation cover class and the 4 lower classes, indicating canopy development of taller trees and dense vegetation. However, in 2010, after an immediate post-fire regeneration flush had occurred, VIR discriminates the understory with the higher mean, assigned the lowest fractional vegetation cover class compared to burned overstory, denoted by the second and third lowest classes respectively. In comparison, NDVI and NBR could not discriminate the immediate post-fire flush of understory vegetation from the burnt overstory due to saturation related to spatial feature configuration.